Firstly, we have to know the power plant layout. What are the parts of a power plant? Well, we know that in our country, almost two-thirds of electricity requirement is fulfilled by thermal power plants. Why they are called thermal? Because thermal means heat, and as heat is being added to generate the steam and to run the turbine. Ultimately, the alternator will be coupled with the turbine, and the steam will, and by the action of the steam, turbine will run or rotate, and through alternator we will get AC power output. So for thermal power plant, some fuel are required. We use fossil fuel like coal. There are grades of coal, and we will know the grades of coal in the third module in details. What are the grades of coal? What is the approximate and ultimate analysis of coal? Like that. Now, so sometimes thermal power station can be called steam power station, as steam is being produced in the boiler. Steam passes through the steam turbine, as I told you. It is condensed. Condensed means steam to water. Steam to liquid will be produced in the condenser and then again fed back into the boiler. It is fed back to the boiler is done by pump. So we know that. So we have learned that there are can be four components, four main components. Accessories will be there obviously, but four main components will be there in a power plant. One is boiler, where the steam will be produced. Then turbine, where by the action of the steam, the blades of the turbine will be rotated and power will be generated. And through turbine, after turbine, condenser will be there. And in condenser, steam will be condensed to water or liquid. And then the liquid will be pumped back by pump to the boiler again. That is the cycle of a steam power plant. And this cycle is called Rankine cycle. Cycle is called Rankine cycle. Now, this is the simple layout of a power plant. Okay, first there is boiler. By boiler, the fuel will be added. Ash, some ash handling is required. After the ash is being generated, some ash handling will be required, or it will pollute the atmosphere only. So then, after boiler, there is steam turbine, and the alternator is coupled. This is the symbol of a coupling. So alternator is coupled with the turbine, and AC power will be generated. So three-phase supply. Then after turbine there is condenser. So steam will come out from turbine and will be condensed. And after condensation it will become liquid again, and there will be a condensate with water pump, and through it again it is pumped back to the then economizer is there. Economizer is generally preheat the water and it will be fed to the boiler again. So cooling tower is the cooling tower. We know that the cooling tower is a part of a condenser. There are accessories actually, but the main parts are four, like boiler, turbine, condenser, and pump. So in boiler, heat is being added, and in condenser, heat will be rejected, and in turbine, what output will be obtained, and in pump, what input has to be given. Okay, so boiler, turbine, condenser, and pump. Here also, boiler, turbine, condenser, and pump. Some accessories are shown here, like economizer, like cooling tower. Here, superheater also will be there as a boiler accessories. It is not shown here. Now let us come to that picture. What are the four main parts? What the four main parts are shown? Boiler, turbine, it is the condenser, and it is the pump. So in boiler, so pump process is shown by 1 to 2, in boiler 2 to 3, in turbine 3 to 4, and in condenser 4 to 1. And it is the Rankine cycle. TS diagram of the Rankine cycle. Now this thing is the vapor dome. This part is the saturated liquid line. This is the saturated vapor line. Now 1 to 2 is pump. Here see 1 to 2 is isentropic process. Entropy remains constant. So reversible adiabatic pumping process. It is called reversible adiabatic pumping process, where the saturated liquid is pumped to the boiler. So what will happen if there is steam? Pump cannot run with steam. So if steam is to be fed, then you have to use compressor, like in refrigerator. Pump can handle only liquid. So it is very much required that after condensation, the whole steam will become liquid. So pump only will operate through saturated liquid. Okay. So 1 to 2 is isentropic compression or reversible adiabatic pumping process. 1 to 2 is shown in the TS diagram. 1 to 2. 2 it is liquid, 1 it is saturated liquid. So it is pumped to the boiler. Then 2 to 3. That whole process is boiler. That part, that small part, is in the economizer. Economizer is shown here. Somewhat preheat is done. See, somewhat preheat is done. Temperature here is increasing. So some temperature is being increased before it is fed to the boiler. So some temperature is to be increased before it is fed to the boiler. So that small process is done in the part or the accessories of the boiler named as economizer. Then boiler, saturated liquid to saturated vapor. This line, this curve represents saturated liquid. This portion of the curve represents saturated vapor line. So in boiler, after economizer, the water will become from saturated liquid to saturated vapor line, where temperature will be fixed. Temperature will be fixed. So that process is constant pressure transfer of heat in boiler. That process is constant pressure transfer of heat in boiler. And then again it is superheated. Again it is superheated. So that portion, after that saturated vapor line between the and 3, between saturated vapor line and 3, that small portion is represent the process in superheated, but the steam is being superheated. Why superheated this steam is required? Because it is quite possible that this line, saturated vapor line, after saturated vapor line, it may possible that some water particles will be there. And if we fed water particles to the turbine, it will damage the turbine blades. So it needs to be superheated to decrease the steam content or to make the steam content 0. That is the superheating process. So at point 3, it will enter the turbine. At point 3, it will enter the turbine, and that process represents again isentropic line. Entropy remains constant, and it is called reversible adiabatic expansion in turbine. So process 3 to 4 is reversible adiabatic expansion in turbine. Now 4 to 1. 4 to 1 process is in condenser. Now see again, if we follow the vapor dome, it's saturated vapor line, and that portion is saturated liquid line. So at the entry point of the condenser, that is 4, steam is saturated vapor, and after condensation, it will follow that path 4-1. It will follow the 4-1 path and will become saturated liquid at point 1. So at point 1, it will become saturated liquid, and it is then pumped back again. to the boiler at point 2. So economizer, boiler, superheater, turbine, condenser and pump. And Q in is the heat input in boiler. Q in it is shown here and shown here, and Q out in condenser. Q out here in condenser. Q out in condenser. So this is the whole Rankine cycle. This is the whole Rankine cycle. This represents in TS diagram and schematic layout of the power plant. Now, calculation of the efficiency. So steady flow energy equation. 1, 2, 3, and 4. 4 processes are shown. And let us come to the pump 1 to 2. The entry point of the pump is 1 to 2. At the entry point of the pump it is 1 to 2. So okay, now let us come to the energy balance equation. We have already learned the Rankine cycle, boiler, turbine, condenser and pump. In boiler, okay, in pump 1 to 2, in boiler 2 to 3, in turbine 3 to 4, and in condenser 4 to 1. 1 to 2, 2 to 3, 3 to 4 and 4 to 1. Here it is drawn also TS diagram, temperature entropy diagram. So now, so first process is 1 to 2 in pump, where Q is 0. Heat input or heat output in pump is taken as negligible or 0. So in pump, if we apply the steady flow energy equation, it will be HF1 or entropy of the feed water. HF is the specific enthalpy of the saturated liquid, the feed water enthalpy. HF1 equals to HF2 minus WP. HF1 is equal to HF2 minus WP, or WP is equal to, it is HF2 actually, not H2, HF2. Why HF2? HF2, HF represents specific enthalpy of saturated liquid. So it is HF, not H, HF2 minus HF1. After that, 2 to 3 in boiler. In boiler, it is generally taken that work input or output as 0. So in boiler, entry point is H2. So H2 plus Q input is equal to H3. H2 plus Q input is equal to H3. So Q input is equal to H3 minus H2. H3 Q input is equal to H3 minus H2. Next comes turbine. 3 to 4 process. 3 to 4 process. But in turbine, heat input or heat output is generally taken as negligible or tends to 0. So in turbine, H3. H3 is equal to H4 plus W turbine or W output. H3 is equal to H4 plus W turbine or W output. So W output is equal to H3 minus H4. H3 minus H4. And lastly, the condenser. Condenser, generally it is not a work input or output device, so work done is neglected here. So in condenser, H4 minus Q out, that heat is out, minus will be there. H4 minus Q out is equal to HF1. So Q out is equal to H4 minus HF1. H4 minus HF1. Now the thermal efficiency. Efficiency is equal to W net. W net means WT minus WP. So as work input is done in the pump and work output is obtained in the turbine, so W net will be WT, W turbine minus W of pump divided by Q input. So efficiency is equals to W net by Q1. So W net is WT minus WP divided by Q1. So WT in from the equation is H3 minus H4, and WP is from that equation HF2 minus HF1. From that equation I am telling only W output H3 minus H4 and W input HF2 minus HF1 divided by Q1. Q1 is here, boiler heat input. Q1 is H3 minus H2. But sometimes to make the calculation simpler, sometimes the work input in through pump is neglected. So efficiency becomes H3 minus H4, H3 minus H4 W out divided by Q in. Q in is H3 minus H2. And all the values are obtained in the steam table, from the steam table. So this is the rough analysis of Rankine cycle, the governing cycle of steam power plant. Now coal. What is coal? In coal-based thermal power plant, coal is transported from coal mines to the generating station. So the means are required. Belt conveyor generally bituminous coal or brown coal is used as a fuel. The coal is stored in either a dead storage or in live storage. Dead storage is generally 40 days backup. Coal storage, which is used when coal supply is unavailable. So in dead storage, coal is being stored for almost 40 days, but when coal is not available. Live storage is a raw coal bunker in boiler. The coal is cleaned in a magnetic cleaner. Coal has to be cleaned because some iron particles will be there. So magnetic cleaner is filter out any iron particles that are present because of wear and tear in the equipment. If we feed the iron particles in the boiler, obviously some wear and tear will be done. So the coal from live storage first crushed. The coal has to be crushed in small particles and will be taken into the pulverizer to make it in powdered form. First powdered coal undergoes complete combustion, thus pulverized coal improves efficiency of the boiler. So pulverized coal improves efficiency of the boiler. The ash, obviously after burning of the coal, the ash will be produced. And the ash has to be properly disposed. Periodic removal of ash is now the boiler. The mixture of pulverized coal and air, preheated air, is taken into the boiler and burnt in the combustion zone. On ignition of fuel, a large fireball is formed at the clean of the boiler. A large amount of heat energy is radiated from it. Heat energy is utilized to convert the water into steam. So water will be converted to steam at high temperature and pressure. And the steel tubes are used to convert the water into the steam. Now flue gases from the boiler may make their way to superheater, economizer, air preheater, and finally get exhausted to the atmosphere from the chimney. Now what is a superheater? Now, from that cycle, that process is superheating process, but the complete moisture of the water is removed. The superheater tubes are hanged in the hottest part of the boiler. The superheated steam produced in the boiler tube is superheated to above 540 degrees C. The superheated high pressure steam is then fed to the steam turbine. So that process, that small process, saturated vapor line, between saturated vapor line and the point 3, it is in superheater. And economizer, you can say the feed water heater. It is a feed water heater, so feed water is being heated before it is fed to the boiler. That part, economizer, is used before the boiler. Before the boiler, somewhere it will be there. By using the flue gas, heat up the flue gas, the water is being preheated and it is supplied to the boiler. So it is called economizer, air preheater. The primary air fan takes air fan and you can warm to the air preheater. Air is being preheated also. Then the next part is steam turbine, high pressure and superheated steam. After superheated, pressure of the steam will be high and will fed to the steam turbine, which cause the turbine blade to rotate. Energy in the steam is converted into mechanical energy. So that at high speed, it will be fed through the nozzle to the turbine blades, and the turbine blade will rotate. So turbine will act as a prime mover. And lastly, the condenser. Condenser, the steam will be condensed to the water and converted back to water, and will be essential because compressing fluid is not the alternator. Alternator is coupled to the alternator. Here will be there. Alternator will be coupled to the turbine, and power will be three-phase supply from the alternator and be generated. The alternator feed water pump. Pump is fed. That is the feed water pump. Pump or circulate water pump, feed water pump. Name same thing as it. So this is the basic working principle of the thermal power station. Let me recapitulate again. So module 1 is the layout of the boiler. Again, boiler, turbine, condenser, pump. 1 to 2 is pump, 1 to 2 is pump, and then pump. It is reversible adiabatic pumping process. And 2 to 3 is boiler. With constant pressure heat transfer, constant pressure transfer of heat in boiler. Then 3 to 4 is turbine, reversible adiabatic expansion in turbine. And 4 to 1 is in condenser, constant pressure transfer of heat in condenser. Heat input is done in boiler and heat output is done in condenser. Work output is obtained through turbine and work has to be given in pump. So the efficiency is also calculated. Efficiency is, we have already learned that Wt minus Wp divided by Q1, and Wt is H3 minus H4, and Wp is Hf2 minus Hf1, and Q1 is H3 minus H2. Ultimately, the efficiency is, neglecting the pump work, H3 minus H4 divided by H3 minus H2. This is the efficiency of a steam turbine power plant.